Hi, in this video we are going to talk about searching algorithms. Searching algorithms are kind of important algorithms. So what will happen is that initially when you will watch this video, then you will go and have some assignments which will be solved using searching algorithms. So what happens is that there are few algorithms that will be solved by direct application of these searching algorithms. There will be few questions in which you will have to modify the searching algorithm, especially the binary search algorithm. You will see that in other videos in which we have solved the problems. Then there will be few questions as you will go ahead is that where searching will be a subpart or it will be a secondary task. Like let's say the first task is to you search it, and based on how you have done the searching, or basically after you have got the results, you have to perform several parts. So this is how the the searching will come in use when you are going through and solving and you are solving the problems. Okay, now let's just see what is searching first. So what is searching? Searching is the process of finding an item with specified properties among a collection of items. The items may be stored as records in database, elements in arrays, text in files, nodes in trees. So today we are going to talk about if we have to search elements in arrays. Okay, so whatsoever we talk about, we'll be majorly talking about linear searching algorithms. The same searching algorithms, as you will go ahead, you will also apply on linked list as well, which is other searching algorithm, which is other linear data structure. Okay, now let's see what are the different kind of searching algorithms. So we have types of searching. Okay, so we have unordered linear search, then we have ordered linear search. I'll remove this notification. Then we have binary search. Then we have hashing. Then we have string searching algorithms in which we use tries, suffix trees, etc. So now these are different kind of searching that happens, and we will be majorly talking about today about these three searches. So this hashing we will talk about later on, and as you can see that this string searching algorithms is generally when you have a string and you have to search for a particular text in a string. So today what we are going to discuss is that let's say you are given a set of items stored in an array basically, and you have to find a particular item in that particular array, how you are going to do it. So first we will see these both algorithms, then we will see how we can optimize it. Okay, so let's go ahead, and this, as I said, hashing and string searching is we will be discussing later on when we talk about string searching algorithms or hashing. Now what is linear search? So linear search is something that will apply on linear data structure, like array is a linear data structure, linked list when you will see is a linear data structure. Basically it looks something like this. Okay, so as you can see it's a linear data structure, it just goes in one particular dimension. Now what happens in unordered is that the items are given not given in any particular order. In ordered it's given in a sorted order. So when I say sorted, which means they are arranged in increasing or decreasing order, so that is called sorting. Again we'll talk about sorting and different algorithms in the upcoming videos, but right now just understand that an array is called sorted when all the elements are arranged in an increasing format or decreasing format. Here we will go ahead with increasing format. We will consider that arrays are arrays are arranged in increasing format. So just like I said is that this binary search, this also works on sorted array. So just like I said that we will see a particular implementation of binary search, and we will do that assuming that the array is sorted in increasing order. Now as I said that going ahead, let's say you are given a problem statement that array is sorted in decreasing order, how will you find a particular element? So in that case you'll have to modify this binary search a bit, but the basic will remain the same. These both are very easy algorithms, and you must have already done this by now if you are sitting and you're watching a lecture of searching. But let's just go ahead and see what is the time complexity and how things are optimized in case of binary search. Okay, let's just go ahead. Okay, so first let's discuss unordered linear search. Let me change color of my pen just to make it more attractive. Okay, so what happens in unordered linear search is, let's say you are given an array 5, 8, 2, 9, 1. So let's say you are given an array, and there, as you can see, that elements are in no particular order. There is no sorting, nothing like that. There is no arrangement that I can find out. And what you have to do is that let's say you have to find 9. like where is 9 in this particular array, or you just have to return the index. Okay, so let's say we have a function, int find element. Okay, and to this we pass the array, and let's say we have the data. We also pass the size of the array, let's say, and we have the data that we have to find out. Okay, so it is pretty simple. What we do in this particular case is that we go through each and every element of the array and we check that whether the element is equal to this particular element or not. If it is, we simply return that index. But now let's say we came to the end of this particular array and we still did not found any element, which means that there was no particular element 9 in this particular array, and we will simply return -1. So we'll return -1 if there is no such element. Now let's just try and do that. So what I'll do is that I'll run a loop for int I equal to 0, I less than n, I plus plus. What I'll do is I'll check if array of I is equal to data, we simply return I. Okay, and if that is not the case, let's say we come out of this particular loop, let's put a bracket over here. Okay, let's see, we explored the complete array, we went through each and every element of the array and we still did not found the element. In that case, what we will do is that we will simply come out and return -1. Okay, so this is how it is. So let's just run it. It is a simple array traversal. Still just let's just run it. So let's say we have 9 here. We check, we start from I equal to 0, we start from here. We check if 9 is equal to 5, no. Then we come here at 1, I increments to 1. We check this is equal to 9, no. We come here, I equal to 2. Then we check again, this is equal to this, no. And then we come here, okay, this is 3. We check this is equal to this, yes. Then we return I. So obviously this particular function will be called from main function, and in the main function we will simply return, we will simply print whatsoever is returned by this particular function. Okay, so now this gets printed. So now what is the time complexity in this particular case? In this case, the worst case time complexity will be when you have to go through each and element of the array. Okay, in this case the worst complexity will be O of n, right? This is the worst case time complexity. What is the best case time complexity? Let's say the first element is the element. Okay, so in that case it will be O of 1. Another worst case time complexity will come when you don't have the element at all in the array. So either it is at the end, towards the end, or the element is not there in the array at all. So in that case you will have to traverse through the complete array. So this is the worst case time complexity, this is the best case time complexity. Generally whenever we do programming, we consider worst case time complexity only. Okay, and also what is the space complexity? We are not using any extra space, any extra array, so we are just having few variables, so it's going to be constant, so it's going to be O of 1. So that is how unordered linear search works. Now let's talk about ordered linear search and let's see how it is comparatively better from this particular search. Okay, so we have seen unordered linear search. Let's just try and see ordered linear search. So let's say we have an array which is sorted and the elements in the array, let's say, are 2, 7, 8. Let me just increase the size of pen, it is being too thin. 9, and let's say it's going to be 12. So let's say this is an array and let's say I have to find 8. So let's say there are two situations, I have to find 8 and I have to find 10. Okay, now what is it going to be? So let's say if I have to find 8, what I will do is that I will do the same thing like linear search. I will go to each and every element, I will see if it is matching with this particular element, I'll simply return the index. If not, I'll just keep on going further. Now what happens in this particular case is that let's say the element is not present in the array. Okay, so in this case let's take the case of 10. So let's say what I'll do is that I'll go here 2, 7, 8, 9, 12. So at this particular place I know that 12 is greater than 10, and if I would have found the index for 10, I would have simply returned from there, but I didn't find any index for 10 right now till now, and also 12 is greater than 10, which means that 10 does not exist. So in this case we came to the last element. Let's take example of let's say 3. Okay, So now if I have to find out 3, what I'll do is I'll go to this place. I'll check if it matches with 3. No, if does not match with 3, what I'll do is that I'll come here. Now I'll check it matches with 3. No. Plus what is happening is that 7 is greater than 3. And we know that this is a sorted array, which means there is no chance that 3 will be available anywhere here. So what I will do is that I will simply return from this particular place only. Let's just try and write the code for this. So let's say the function is int sorted linear. Let's call it sorted linear. Okay, let's say we have the array int arr. Let's say we have size of the array. Let's say we have the data. Okay, now what I'll do is that I'll run a loop. So let's say I run a loop for I equal to 1. We have to write it int I. Let's just go back. Let's write int I equal to 1. Int I equal to 1. I less than n. It's going to be 0. My bad. I plus plus. Now what I'll do is that I'll start checking if arr of I is equal to data. In that case, what I'll do is that I'll simply return I. Okay. If that is not the case, we'll check if arr of I is greater than data. We will simply return -1. There's no point of going ahead because I know that it doesn't exist. And let's say we came outside of the loop. Let's say the number was 30 or something like that. In that case, none of these will get executed. We'll come outside the loop and we will simply return -1. Okay. So now this is how it's going to work. And what will be the time complexity? In this case also, the worst case time complexity is going to be O of n. Okay. Because at the end of the day, we saw that worst case is that either it is the last element, or let's say the last element does not exist at all, or for that matter the data, sorry, my bad, the data does not exist at all. In that case, we are going to traverse the whole array. So the time complexity is going to be O of n. What is the best case time complexity? Is going to be O of 1. And what will the space complexity? It's going to be O of 1 again, because we are not using any extra space. So as I said that in this case, we don't have very much optimization in the worst case. But what happens many a times is that when you're writing a program, then these kind of tricks work, okay, based on what is the time complexity. So you can try this as well. But the thing, but the algorithm that is going to optimize even the worst case time complexity, we will talk about that, and you will be using mostly that particular algorithm. So that algorithm is known as binary search algorithm. Very interesting algorithm, will be very much useful. Let's just go ahead and see that. So now we are going to talk about binary search algorithm. So first let's try to understand that what is a binary search algorithm, then we will write the code. Okay, so what is binary search? So now let's say you are given an array. Again, one thing to keep in mind is that binary search algorithm just works on sorted arrays because of the concept it uses. Let's see the concept. So now let's say there is an array, let's say 23, 45, 67, 89, 100. Okay. Now let's say I have to look for 45. Okay. Now what I'm going to do in this, what happens in binary search is that I start with the mid element. Okay. In the linear search, we saw that we started from the beginning and went till end. But here what we will do is that we will start with the mid element. So the concept is that I look for mid element. Now there are 3 cases that mid element is greater than this particular data, or the mid element is less than this particular data, or mid element is equal to this particular data. Okay, these are the 3 scenarios. Now let's see what happens in these 3 scenarios. So let's say if mid element is greater than data, let's say I have to find 67 and this is 45, which I can clearly see is that greater than the data. Now, is there any possibility that this 45 will be coming in this particular half of the array? Is there any possibility? No, there is no possibility, because all the elements after this particular element will be greater than this particular element. So there is no point that this element will exist in this particular half. So what I will do is that I'll continue my search in the first half. Okay, so the idea is to keep on dividing the array into half for each and every search or each and every iteration, and this is based on the concept of divide and conquer. We will talk about divide and conquer in much more detail. For now, just try to understand that this is what is divide and conquer. Basically, we divide our problem into sub problems, and most of the time what we do is that in this case, like, we are rejecting the rejecting the second half. So in case of divide and conquer, the division might not happen in exactly half. So we will talk about divide and conquer, but here we are dividing the problem statement into exactly half. So this is how I'm trying to optimize. What I did was that I divided into half. I saw which half is useful for me and which half is not useful for me, and I simply rejected that particular half which is not useful for me. Okay, now what I'll do again is that again I'll calculate my mid. Now in this case, this is the array in which I'll do the searching. This is my searching array. Now what I'll do is that I'll again calculate mid. So how will I calculate the mid? So this is 0, 1, 2, 3, 4. So what I'll do is that I'll calculate the mid using the formula 0, 1 plus by 2. So basically this is low, this is high. So this is how we calculate the mid. In this case, it's going to be low is going to be 0, or the starting index of the array, and high is going to be the end index. So the starting here is 0 and end is 45. Sorry, end is 1. So now what is 0 plus 1 by 2? It's going to be 0, right? So now what I'll do is that this is my mid now. Okay, now again I'll do the same thing. I'll check if mid element is greater than data, mid element is less than data, or mid element is equal to data. In this case, this particular thing is happening. Okay, so now we see that 45 is greater than 23. So what I'll do is that I'll continue my search in the next half. So now my next half is this particular half. So there is only one element. So now at this place, what happens is that my low becomes 1, my high becomes 1. So my mid becomes 1 plus 1 by 2, which is equal to 1. Now I check that whether the mid element is equal to data. Yes, the mid element is equal to data. So I simply return this particular index as my answer. Okay, so this is the agenda, that I divide the array into two parts at each and every step, and then I take the decision that I have to take the first half or the second half. Okay, if I take the second half, then I'll do my calculations accordingly, and if I do the first half, I'll take my calculations accordingly. So this is how it is. Let's take one more example. Let's take 89. Okay, so if I take 89, what will happen is that again I'll start with this particular place. This is my mid. How have I calculated this mid? It is 0 plus 4 by 2. At any time I'll keep on calculating the midpoint. Okay, now let's say it is going to be 0 plus 4 by 2. Now what I'll do is that I'll check this is greater than 89 is greater than 67. Now there is no point that 89 will be somewhere in this first half of the array, so I will reject it. Now I will go ahead. Now this is my array. This is my new low. This is my new high. So what is going to be my mid? It is going to be 3, 4 plus 4 by 2, which is going to be 3. Okay, so we will always take the integer, so we'll take the floor value. So it is going to be 3 plus 4 by 2, it is going to be 3. So now this is my mid. This is my mid at this particular point. And now we will see that this element is equal to this particular element, so we will simply return this particular index. So this is how binary search works. So let's first write down these steps, and we will also see the time complexity for this. So first let's write down the steps we did. So first thing what we do is that we will calculate our mid. Okay, and mid is also always equal to low plus high by 2. Okay, now what we will do is that we will check. We will have certain situations. If mid is equal to data, we will simply return mid. If mid is greater than data, we will simply update. What we will update? Just think, mid is greater than data, which means the search will continue in second half or first half. just think around it, that it's going to be continuing search, the search will continue in second half or first half. So this is the case, mid is greater than data, so the search will continue in first half. How my search will continue in first half? So what will happen is that low will remain as it is, okay, and my high will update. What will be my high? Now my high will be mid minus 1. So after this I'll update my high to mid minus 1. Okay, now what is the other thing that we will do is that if none of this is true, which means that we are falling in the category where we have to keep the search in this particular area. So when we are searching in this particular area, how the values are changing? High remains as it is, my low will change. Okay, my low will change, my low becomes, it's going to be mid plus 1. So this mid is the index of the mid element, okay, mid plus 1. So, and these are the steps that we have to follow, and we have to keep on following these steps. Either we get our element, the element that we are searching, or let's say what if the searching element is not there. Let's say we have to, we don't find our searching element, or let's say there is something called 60 and 60 is not there. So what will happen is that in case we come to a place where we don't have the element in this particular array, we have to stop somewhere, right? We have to stop somewhere. So let's take example of 60 and see that how we are going to take care of 60 and what will be my base condition. So basically we will keep on running these steps unless we get our element, we see that okay, we found an element and we return, or we get to know that okay, the element does not exist. So we will see that how do we find out that element does not exist. Let's see the scenario, what happens if element does not exist. Okay, so let's say we have again the same array. Okay, I forgot the array, let me take a random array, 23, 45, 69, 80, 100. Okay, and now let's say the element that I have to find is 60. Okay, so now in this case this is the mid. Okay, this is my mid, low is 0, high is 0, 1, 2, 3, 4. So initially my low is 0, high is 4. Okay, and my mid is 2. Now I see that mid is greater than 60. So I'll continue my search in this particular half. So my low and high gets updated. My low becomes 0, my high becomes 2 minus 1, it becomes 1. Okay, now again we look for 45. Okay, so sorry, my bad, my mid is going to be 0 plus 1 by 2. So this becomes my mid. Okay, again now what is happening is that 23 is not equal to 60. Now I'll continue my search in this particular half. Okay, so now what happens is that my low becomes 1. So when I continue this half, what will I do is that I'll update my low to mid plus 1. What was my mid? My mid was 0. So mid plus 1 becomes 1, and my I update my high. Okay, my high also becomes 1. Now I again check. I check that what is happening is that 45 is still less than 60. 45 is still less than 60, right? So what will I do is that my tendency is that I will update my high to, I'll update my high to mid minus 1. This is my tendency, that if this element, okay, my bad. So in this case, what is happening is that this 45 is less than 60. So what I'll do is that my tendency is to start searching the element in the second half. Start searching the element in the second half, because 45 is less than 60. So I'm assuming that in the second half the element will be present. So I'll let the high as it is. What I'll do is that I'll update my low to mid plus 1. And what was my mid here? My mid is equal to 1 plus 1 by 2, which is 1. So now what happens is that after this operation, my low becomes 2 and my high becomes 1. So now what happens is that at this particular point, my low is greater than high, which is not going to happen. So as soon as you get your low greater than high, it means that element does not exist in your array. So the steps that I have mentioned, the 3 steps that I mentioned, that is going to run only till low is less than high, or for that matter if low is equal to high. So if at any point we get that low is greater than high, we simply return minus 1. So this is my base condition. Okay, so we have seen the steps and we have seen what is my base condition, or till when I am going to apply my logic, or till when I'm going to keep on searching for the array. Now what happens is that the code that we have seen, or for that matter the steps that we have seen, has got two implementations. One is iterative and the other one is recursive. Okay, so let's go ahead and see both the implementations. First we will see implementation over here, and then we will just go ahead in the IDE and then we will write the proper code. First let's just see both the implementations. Okay, and when we see the implementation, then we will also see what is going to be the time complexity for this. Okay, so we have already seen that what are the steps we are going to follow in order to write a binary search code. Okay, so let's just try and convert that steps into code. So here we won't follow any language, we'll write a generic code, and while we are writing the language specific implementation, we will obviously see the syntax and all. Okay, let's just go ahead. So now we will have, let's say, the function int binary search iterative. Okay, I will take the parameter array, int array. Okay, then I will have the length int n, and then I will have the data that I have to search. Okay, I see these are the parameters. Now what I'll do is that I'll calculate my low. So our low is going to be 0. Okay, and our high is going to be n minus 1. Okay, now I'll run a loop. So we have seen that the loop will run, or we will keep on continuing our search till we have low less than high. So what happens here is that we will keep on running the loop till we have low less than equal to high. Okay, so as soon as low becomes greater than high, that is when we will stop searching. Till we have low equal to or less than high, we will keep on continue the search. Okay, now here what we will do is that we will calculate our mid. So we will have mid equal to low plus high minus low by 2. So in case you are wondering why we have done this, so this is equivalent to low plus high by 2 only. But in case of low plus high, what we do is that we add both of them. So in that case, what happens is that if, let's say, low is a very large number, or let's say it's the maximum integer number, or this is maximum integer number, in that case what will happen is that integer overflow will happen, or for that matter we will get similar kind of errors. So in order to avoid that, we write it in this particular format. So though that thing is completely not eliminated, but we can still avoid it to a certain extent. So that's why we write in this particular format. Okay, so now let's say we have int mid equal to low plus high minus low by 2. Okay, we check that if array of mid is equal to data, we simply return mid, else if array of mid is greater than data, we will update our high to low minus 1, my bad, mid minus 1. So why are we updating our high? So if array of mid is greater than data, which means we had a data and let's say this was mid, let's say we have 1, 2, 3, 4 and we had to search for 2. So 3 is greater than 2, which means that I have to search in first half. So that is why low will remain as it is, high will get updated to mid minus 1. Okay, now either in this situation we get the array, we get the data, or we search in first half. If none of these is true, the only place we have to go is that we have to search in the second half. So if none of these is true, we will simply do else low equal to mid plus 1, which means high will remain as it is and my low will be the next element. So I'll search in this particular, let's say there's one more element over here, so I'll search in this particular array. Okay, now this is how it is. So this concludes my loop. Now let's say if I have already found the data, we will somewhere return mid, return the index. But now if I have completed this loop and I'm out of this particular loop, which means we haven't found the data. So in that case, we will simply return minus 1. Okay, this is how the binary search works. Now the question is, what is the time complexity? So the time complexity depends upon how many times this particular loop will run. So there are two things to keep in mind. First, every time what we are doing is that we are reducing the input size by 2. So initially it will be 1, then n by 2, then n by 2 to the power 2, then n by 2 to the power 3. Okay, now let's say this loop runs k times. Okay, so this loop will run until n by 2 to the power k is equal to 1. Okay, let's try and solve this. N is equal to 2 to the power k. Let's take log on both the sides. So this gives me k equal to log n. So this is going to be the time complexity. So the time complexity of this approach is O of log n. Okay, so this is the time complexity. This is worst case time complexity. The best case might be the, like, you get the element in the first go, so it might be O of 1, and also the space complexity is O of 1. So but generally, we go ahead with the worst case time complexity only. Okay, so we will see the recursive approach and we will also see the implementation of this. So this particular thing will remain as it is. We will just add the C out, C in, or the system in thing when you're writing the code. Okay, now let's just go ahead and write the recursive code. So let's say this is my recursive code. The function is int binary rec. Okay, what are the parameters that we will pass? We will have the array, we will have the low, we will have the high, and we will have the data. Okay, so while you are writing the recursive code, we have to take care of the parameters, we have to take care that when the recursive call will happen, and the base condition. So let's see what is going to be my base condition. So the base condition is that if at any point, it will be vice versa, if at any point low is greater than high, we will simply return -1. Okay, which means the data does not exist in the array. Else what we will do is that we will calculate our mid. Mid is equal to low plus high minus low by 2. Okay, now what we will do is that we will check if arr of mid is equal to the data. We will simply return mid, which means we found our index. Else what we will do is that we will check if, or what I'll do is, let's remove this else if. We will simply have if arr of mid is greater than data. So in this case we have to do the searching in first half. So what we will do is that we will simply do return. We will call this function again. So the function is binary rec. So here the recursive call is happening. So we will have binary rec int. We will pass the array arr comma low. So low, what will be my low? Low will remain as it is. My high will be mid -1 because I have to search in the first half now. Okay, and my data will remain as it is. Okay, now let's say if this is not the case, this is not the case. It is not equal to data, it is not greater than data. What will be the case? The case is that mid is less than data. In that case, what we will do is that we will search in second half. And in order to search in second half, what we will do is that we will update our low to mid +1 and high will remain as it is. So if none of these is true, we will simply return binary rec arr comma, we will have mid +1 comma high comma data. Okay, so now this is how my binary code will work in case of recursion. So now what is the time complexity for this? So the time complexity for this is going to be, so if we see the Tn will be 1 in case n is equal to 1, else it's going to be T of n by 2 plus C. So what will happen is that in each recursive call, we divide the problem into half, okay, and there's some constant time that is being taken in each and every recursive call. So this is what the equation is for n greater than 1. And if you solve this either by recursive tree method or you solve this by master theorem, you will find it that the time complexity is going to be O of log n. Okay. So now let's what we will do is that let's just go ahead and write the proper code. Basically the proper code. By that I mean is that we'll write the code in the compiler in a specific language, and let's run and see if we are getting the right output. Okay, so one more thing we can do before doing that is that we can just simply try and dry run this recursive code. In case you are clear with recursion, you will understand this really well. In case not, let's just try and dry run it for a very small example. So let's say I have an array. I'll take a small array. It is 2, 3, 7, 12, 15, and let's say I have to find out 12. Okay, so now let's see how the code works. So initially what will happen is that we will have low equal to 0. So from main, when this particular function will be called, we will give the value of low as 0 and high as n minus 1. Okay, so we will have low equal to 0, high equal to n minus 1. So now what happens is that we check if low greater than high. No, that is not the case. We calculate mid. So my mid will be high plus low by 2. So n minus 1 here is going to be 3. 0, 1, 2, 3, 4. So it's going to be 4. So my mid becomes 2. So we check arr of mid equal to data, which is not the case. This is the mid and this is not equal to data. So what I'll do is that I'll come here. I'll check if arr of mid is greater than data. Is this the situation here? No, arr of mid is not greater than data. So we come back here. So it is that since both of these are not true, we will simply return binary rec arr mid plus 1 high data. So now what will happen is that my low, this mid plus 1 will go to low. So now my low becomes 2 plus 1 3. My high remains as it is. My high will be 4. Okay, now let's come back here. We have if low is greater than high. No, that is not the case till now. We again calculate mid. So what will be my mid? Mid will be 3 plus 4 by 2. Okay, so it's going to be, or you can just calculate it in this way. So it's going to be 3 plus 4 minus 3 by 2. So this is going to be 3 plus 1 by 2. Basically this is going to be 6 plus 1 by 2, which is 7 by 2. So this is eventually the same thing. So this gives me 3. So now my mid becomes 3. Okay, so now we check arr of mid is equal to data. So we have 0, 1, 2, 3, 4. So is this equal to data? Yes, this is equal to data. So we simply return. Okay, so now what happens is that when we return, where does this value goes? So initially what happens was that the function was called from main, but the value won't go directly to main. This is something that you should know. When we return mid from here, it will go to the calling function. So what was the calling function? So the calling function was, the last time the function was called, it was being called from here. So what happens is that it comes back and it returns to this particular place. Now as you can see is that this particular function, okay, this gets the value as 3. Okay, the mid was 3. Now here we have return 3. So when we do return 3, again what will happen is that it will go to the calling function and that will eventually go to the main function. This is something that you should remember. Also one more thing you should know is that we have return over here. So what happens in case of recursion is, this is case of recursion not binary search, is that let's say if return is not here, we have simply binary rec or something like that. So in that case what happens is that whatsoever is statement after this particular statement, that gets executed. But if return is here, then that won't be the case. So you must have seen that when the function called function returns the value, and what happens is that the next statement gets executed, but that does not happen if you are calling that function with return. Okay, so this is a very basic thing that I want to tell you. So this is how the recursive function works. Make sure you try run on your own as well to understand the things better. Now let's just go ahead, write this in IDE, write this in an IDE and try and run it. Okay, so we have seen till now the recursive as well as iterative implementation of binary search. So we will do a similar thing here. It's just that we are going to do it in a Java language. Okay, so let's just go ahead and do that. So I have written the skeleton for search iterative and binary search recursive. I'm going to implement both. Here what I'm doing is that we have the main method. So here we will have the scanner and then we are going to take input using this SC object. Okay, so here we have the array. Here we are taking input n. Then we are taking all the array elements as the input. And then we are taking this data as the input. So then we are calling binary search iterative. Whatsoever we get from here, we are simply going to print it. So here we are passing the array. low, high and data. So here we are let's first implement this binary search iterative. Here we are taking this array, then we have low, high and data. So here I am giving low, high as the parameter. You can simply give the length of the array, okay, which is going to be n, and you can calculate low, high using that. Okay, let's just go ahead. So now what I'll do is that I'll directly jump into the loop. So we will have the loop will run till we have low is less than equal to high, okay, and then we will have a loop. Okay, in this what we do is that we calculate mid. So we'll have int mid is equal to low plus high minus low by 2. Okay, we check if our mid is equal to data, we will simply return mid. If that is not the case, we check if our mid is greater than data. What we do is we simply return, no, we don't return here. I was just in the flow of returning stuffs. Anyways, in this case, what we do is that if arr of mid is greater than data, in this case, we continue searching in the first half. So we will update our high to mid minus 1. Okay. Now, if none of these conditions are true, which means we have to continue our search in the second half. So we will do else low equal to mid plus 1. Okay, so this is my code, and in case we come out of this particular loop and still we don't have anything, so still if we have the data at one or the other place, this will get executed and will return. If we are out of this particular loop and we are here, which means we haven't found the data, so we simply return minus 1. Let's just go ahead and run this. Okay, so I got the output as 4. Let me run it again. I'll take the same array, but I'll take different position. Let me take it 2. So I get the right answer. So this seems to be working. Now let's just go ahead and write code for recursive. I'll change it here. Okay. Now, so what I'll do is that first I'll have the base condition. So the base condition is that if low is greater than high, we simply return minus 1. Okay. Now, what we will do is that we will have mid. We will calculate int mid is equal to, let me just copy from here. Let me copy the entire thing. Okay. So we have if mid is equal to low plus high, mid is equal to low plus high minus low by 2. We check if arr mid equal to data, we return mid. If that is not the case, else if arr of mid is greater than data, in this case, we will again call this function. We'll have return binary search recursive. We'll have the array. We will update our low to. It will remain as it is. There won't be any update of low. There will be update of high. My high is going to be mid minus 1, and we'll have the data. Okay. And if none of these conditions are true, we will simply return. We'll have the array. Our low will change in this particular case. It's going to be mid plus 1, and high will remain as it is, and we will have the data. Okay, so this is the code. Everything looks fine. Let's just go ahead and run this. I hope I've changed it here. Yeah, I'll run this here. So let's try the same input. 1 2 3 4 5 5. I get 4 as the output. Let's run it again. Let's say we have 5. 1 2 3 4 5. Let's put 1. Okay, so we get the same output, which means it's working fine. So make sure you guys try on your own as well. Don't just see the video. Try on your own, understand it well, because this is going to help you a lot in solving further problems. And you might have to modify the binary search as well, especially the recursive binary search. You might have to modify. Okay, so if you don't understand it well, you won't be able to modify. By modify, I mean that you might have to change the parameters, you might have to add some conditions. Many problems are solved using that. Okay, so make sure you do it on your own and make sure you write the code. Okay.